All right, in the previous lecture, so there was this typo on this diagram over there, and I didn't notice, and that got me confused. So those directions, basically perpendicular to the surfaces, should be minus the unit vector for the coordinate system. So because the perpendicular vectors always are defined outward, right? So it should be minus. So you will have a minus, basically force T in the direction of minus E1, delta A1, and so on and so forth. And then you use Newton's third law, saying that the force in the negative direction is just the negative of the force in the other direction. So you will get the minus basically out, right? So that will give you something that is very unique. It has two directions with it. E1, T, E2, T, E3, T. So that's the typical stress tensor that you are dealing with. Okay. So for this class, it will be a short lecture because you are going to have a quiz. I'm going to talk about coordinate systems. So basically, just a review of the curvilinear coordinate system. So think about a position vector that you can define the position of a point in a space in a three-dimensional. So those coordinate components Q1, Q2, Q3 can be in a Cartesian coordinate system can be X, Y, Z. Okay? You have seen cylindrical coordinate systems, right? What are the components over there? What?
X, Y, Z.
In a cylindrical coordinate system. R what? R theta Z, right? So we'll talk about that. But those Q1, Q2, Q3 are those components. And depending on the problem that you are working, you may be using one of those three major coordinate systems, or you can basically come up with your own coordinate systems, right? So there are some definitions. So for example, what are the coordinate lines? These are the curves where two of these components are constant. So basically, if you consider this line here, as long as I'm on that line, Q1 and Q2 are constant. So that's the coordinate line for Q3. So you can do the same thing for the other coordinate lines here and here. So these are other coordinate lines that you are going to have. Typically, we use also axis at a given point. So axis direction comes from the tangent vector at the basically point that you have in the coordinate line. So the direction of the axis at this point here, so it's going to be a tangent, let's say in the direction of Q1, so I need to draw a tangent line here. So I need to draw another tangent line for the other coordinate line that I have. So those three directions gives me the axis direction. So in a general curvilinear coordinate system, it's curvilinear, we mean that the coordinate lines are not lines. Basically, they can be curved like that. Your axis direction at each point can be different because your tangent to the coordinate line can change. In X, Y, Z coordinate system, it's the same. Because your axis, basically, the coordinate lines are straight lines. Okay? So the basis vectors, so far we just introduced basis vectors, right? We didn't say where they are coming from. They are coming from the coordinate, how your coordinates and the position vectors are changing. The derivative of the position vector with respect to each of those components that you have in your basically coordinates system is going to give you the basis vector. Okay? So EIs that we have are basically the derivative of R with respect to QI. So that's the definition. So for some simplicity and make the calculation sometimes easier, we define other parameters like the scale factors. Basically, scale factors are the magnitude of this EI. Okay, so in many books, they use this HI as a scale factor. Now you can use that to define it as a basically unit vectors. So you can scale it by HI, and again, HI is just the magnitude of that vector, right? So you scale it with that and calculate the unit vectors. And you can use this method to exactly calculate ijk vector, or in the coordinate system, like cylindrical coordinate system, as the unit vector as r hat, theta hat, or z hat, okay? One important thing is this, basically the line element that you define as the basically a small segment for the line integral that we use. These are going to be hi, dqi, ei. So this will have three components in 3D system. So this goes to 3 in 3D system. And important quantity of your space that you are defining is this metric tensor component, Gij, which are the dot products of your basis vectors, ei.ej. Okay, so if you are 3D component system, then you will have 9 components for Gij. It's just definitions, okay? Using this method, basically this framework, then the surface element or volume element for any coordinate system, you can cast it based on that HI and QIs that you are defining, right? So you are not limiting yourself to spherical or cylindrical or other type of geometry. As long as you have a relationship between the position vector, basically the position of the point in the space, in terms of the components of the system that you define, you should be able to derive all of this. So surface, basically, surface element dA, for example, is going to be hi, hj, dqy, dqj. So these are basically for a surface that the other component is constant. So think about a surface element. You have 3 different dimensions, right? So you need to define surface in which plane. Let's say if it is r theta phi, in a spherical coordinate system, which surface I'm considering? Is it r theta or r phi or phi theta? Which one it is, right? So that's why you have that type of relationship over there. Always one of the coordinates are constant when we are defining the surface element. Arc length also is a very simplified, so ds we use dsi, hi, dqi in the qi direction, and the volume element is going to be h1, h2, h3, and multiplication of all of the 3 element differential change in the q1s, right? These are the definitions. So if you use this, in the basically now, if you look at the Cartesian coordinate system, so you have x, y, z, and that's the point in the space, right? So my q1 is x, q2 is y, q3 is z. This is how I define it. You can define it the other way if you want. The unit vectors are mutually perpendicular to each other. The scale factors are 1. And it's pretty straightforward coordinate system, and we have used it a lot in the calculation. So nothing is special about it. Now, I'm going to show you the cylindrical coordinate system. Okay. Again, I have a point in the space. So basically, I'm interested in this point, right? So the projection on the xy plane is this line. The distance of this line from the center is going to be my radius, radial, or the polar coordinate, r. The angle that is making with the x-axis is going to be theta. So this is the second element in my coordinate system here. The third one is easy, is the z value. Z value that it's exactly same as what you would see in a Cartesian coordinate system. Okay? And you can define the unit vectors based on the method that we had. You are going to look at the derivative of how the position vector is changing by changing that coordinate component, right? So easy, z hat is same as the k in the Cartesian coordinate system. It's exactly that. Then you will have r hat, which is basically goes this way. So if I can use this laser point, this is r hat. Then theta hat is going to be tangent to this, basically the circumference of this circle that you have over there. So that's the theta hat. Okay. So coordinate system, if you consider it in an r theta plane, is going to have a basically curved space, obviously, because you have a circle, right? And in the z direction, still it is this simple linear case that you see in the Cartesian coordinate systems. Okay. So scale factors 1 for basically r, then h2 is r, h3, the third one, corresponding to the z coordinate is also 1. So using that h1, h2, h3, you should be able to get the basically area or the volume elements. Next one is the spherical coordinate system. So now, instead of just relying on the z coordinate that you had from Cartesian, we are going to forget that. The radial distance between the point to the origin is going to be the first element, r. Then I have two angles. One is the polar angle, is the theta angle. So theta basically runs from 0 to pi. So this is theta. So it goes from this side to this side. So theta 0 to pi. We call that the polar angle. Then we have the azimuthal angle. Azimuthal angle basically is, you can think about it as a circle in an XY plane, let's say, right? So if you get the projection of this line here, so I have phi angle goes from 0, starting from here, and it has 2 pi basically limit for it. So using that and considering this limits for theta and phi, I can build my three-dimensional space. That's the idea. Okay, and those are the typical direction of the r hat, theta hat, and the phi hat for that particular example that we have. Okay, so it's a fully curvilinear coordinate system where h1 is 1, h2 is r, and h3 is r sine theta. Any questions so far? Very good. So yeah, we need to know this because some of the differential equations that we are going to derive and solve is sometimes it's in the cylindrical coordinate system, sometimes in the spherical coordinate system. So you need to be familiar with these different variables. Okay. The next concept as an overview from your mathematics classes is fields. What do we mean with field? Have you heard fields named in mathematical concept? No? Okay. Gradient, curve, yeah, okay, good. So a field basically assigns a value to every point in space. We can have different types of fields, like a scalar field. Let's say I'm measuring the temperature of this room at different points, right? So at each point, I can put a thermometer, right? And that function can determine a temperature, which is scalar in this case. Depends on the x, y, z, and probably also time, the time of day that I'm measuring the temperature, right? So that basically, this function that returns me information about the space is a field. Okay, so temperature is one example. Any other example that you can tell me? What is scalar field? Brightness, okay, yeah, of course. Yeah. Humidity, right? Same thing. Whatever that depends on the x, y, z, right? And in this particular, I don't want to have it as a vector, just scalar problem, right? So similarly, you can define fields or find fields that returns you a vector. So you can, if you think about this, the first example, the phi that gets us the temperature. So think about it as like a function. X comes in, y comes in, z comes in, times comes in. It gives us one thing, temperature. That's the meaning of this scalar field, right? Now in the case of vector field, same thing. So it's a vector field. So x comes in, y comes in, z comes in, maybe time is coming. It gives us a vector also, x, y, z. Or more parameters, doesn't matter, right? Also time. Different components, right? So it is a multi-variable thing. Example, velocity field in a fluid. To exactly know the velocity field, you need to know exactly what is the x, y, z. And if it's an unsteady process, time to measure the velocity. And velocity has 3 components, right? So that's an example of the vector field. Good. Tensor field is going to be your stress. Stress tensor is a tensor field. It gets x, y, z. It gives you 9 components. Okay, here are some more basically information about the scalar field. We'll start with the scalar field because they are easier. So if you are in n-dimensional space, so you will have n-dimensional coordinate variable, q1 to qn. Usually they are continuous, differentiable over the domain of interest that we have. There is a definition of an isosurface or level surface when we basically say that this, whatever function it is constant. Let's say, think about the temperature example, right? So I want to find a level surface of a thermometer that I have. The temperature is 25 degrees C in all over the place, right? So I'm going to find all the 25 degree temperature, then connect them together, create a surface. Some hyperdimension surface that I can create, right? So that's the idea. So basically, in most cases, in 3-dimensional surfaces that we are, 3-dimensional space that we have, the surfaces are going to be a 2-dimensional, basically, object in this space. Now, the key point here is, if I have these 2 surfaces, okay, let's say phi equal to C1 and phi equal to C2, and that's my phi function, right? So, and I want to define the derivative of phi. How should I define the derivative here? For 1-dimensional functions, it was easy, right? You were just taking the, let's say I have y equals to f of x, right? So easily you can differentiate f versus x, and then that's it. That shows a change in the variable f or function f, right? But how do you define the derivative here? Because for sure, think about these are 2 planes that are adjacent to each other. If I want to go from this point, basically this surface to this surface, I can go this way. follow this line, L1, let's call. I can go also this way or other directions. So how should we define derivative then? So what do you suggest? We do d phi by dl. And L is just your direction, right? Okay. Basically the length that you are considering. Let's define this as d phi to dl as a limit. So just definition of the derivative, right? Let's call this L. So I'm going to consider this guy, but this is not going to change anything in my derivation, right? So it is going to be value of the function over there is this value, phi at point m prime minus phi at point m. So I'm going, basically, this is the step that I'm taking. The length is going to be m divided by m prime. And to make it a derivative, I need to calculate this as limit of m prime goes to m, right? Squeezing it together. So that's the textbook definition of the derivative. Are you okay with the definition of the derivative here? Okay. So now, what can we do about phi of m prime? Let's say we are in a three-dimensional space, x, y, z, right? So here, let's put it as x1, x1, x2, x3 points, right? So what we can say is phi of m prime, the value of the function over there. Instead of writing it based on this difference here that I have, I can write it as x1 plus the length of m prime times cosine of L vector and x1 as my basically first component of that, right? For phi of m here, what I have, it has another x1, x2, x3, right? So I'm basically what I'm doing, I'm replacing it in terms of the coordinate of x1, position of x1, and then I'm adding that element over that I have. The jump that I need to have in the delta x in the x direction, delta x2, x3, right? So in terms of the length of the prime and then angle between the L and x1, basically coordinate direction that I have. So similarly, I can do the same thing for the second component. So x2 plus prime cosine L and x2 plus, not plus, the third component is going to be x3 plus prime cosine L x3, okay? So remember, this guy here basically was phi of m prime is just phi x1 plus that delta x1, x2 plus delta x2, x3 plus delta x3, okay? And I'm just replacing it from what I know from the geometry. Or maybe this guy should be here, right? So, okay. Because this is the second one, it's here. So we are using the projection of that line element over there, basically the two connecting points between M prime and N, and considering that projection of it on our axis, x1 or x2 or x3. Okay, so that was the toughest part. Now, I have the information about the value of the function phi at M prime point based on the information in the M point, which is x1, x2, x3, and the direction between the M and M prime, right? So the question for you now is, can I approximate that, basically, this part? Can I magically approximate that part? Basically motivated by one-dimensional calculus that I know. Think about separately. So think about, you have a one-dimensional function like phi, which is only you are looking for finding phi of x1 plus mm prime cosine L x1. That's the problem that we're focusing. We're focusing on this part, let's say. So how I can write this part differently? I will give you a clue. I want to take, basically, I want to have something like phi x1 plus something else. I want to separate this two things. It is not broken. Phi x1, yes. Plus. You're in the right track. Not Laplacian. So how did you, in your, okay, let me find a place to write this because this is going to take the space here. So how do you simplify this? Phi is a function. You have only one variable. You have basically, you want to cast it in terms of phi of x. Delta x times d phi dx, right? Do you remember something like Taylor's series? Any questions? So we are going to use that. Right? So if I just write it in a compact way, because I don't have much space here, then I can say that phi of m prime is going to be phi of m, which is phi x1, x2, x3. So I'm going to all gather together, all of them. So I have d phi dx1 times cosine L vector and x1 plus d phi dx2 cosine L vector and x2 plus d phi dx3 cosine L and X3, and all of this are going to be multiplied by M prime, right? That is a constant. So that is going to be the value of the function at the M prime point. So you may say, okay, this is not 100% right, okay? Because the idea that I have written over the top in the blue color, it has some error in it, right? It's an approximation. So if you think about it, there are terms of order of delta x squared that I'm just setting them to 0. Higher order approximation. So this is important that we need to consider here, that this step size that we are taking is so small, and it is okay because that's the definition of the derivative, right? So I just want you to remember that part, right? So this approximation that we have here, it has other terms that involves the second derivative of phi with respect to x1, x2, x3, third, fourth, but we don't care about them because they are so tiny. When we are calculating that limit, they don't matter, right? So I have that relationship. Okay, so if I use that, then what will happen for my d phi dl? So if you add that definition in that limit, right? You see, phi m's are going to cancel each other. Do you see that? Phi m's are going to cancel each other, so I will have this term here. M prime multiplied by this huge thing. M prime are going to cancel each other, right? So I don't need to worry about division by 0 anymore. Then I will have this guy. This is a d phi dx1 cosine L x1, d phi dx2 cosine L between L and x2, and the same thing for the third couple, right? So what's that? Any suggestion? You have seen it before, I'm pretty sure. I need something easy to write, compact. It's too long. You can use the L vector, by the way. Because L is the definition, is the direction that we choose. I'm interested in finding the temperature gradient, let's say, in this way or that way. It might be different. I might have an AC thing over there, so that might be colder, right? So not necessarily in all directions are the same. That we define the direction. What? No suggestion? Nothing? Okay. So this is going to be L dot. Do you see the dot product here? Kind of a dot product. Gradient of phi. That's how you define actually the gradient vector. So if it is an n-dimensional space, it's the same story, right? So 3D like this, you can do 2D, you can do n-dimensional. So that's actually basically a dot product between this d phi dx1 and some basis vector associated with, and the L vector, okay? So in general, in the curvilinear coordinate system, so the way that you can define a gradient, you can use those HIs that we have defined as scale factors, and basically you can define it as a d phi dqi times ei. Let's say I'm in a Cartesian coordinate system. So in the Cartesian coordinate system, gradient of phi is going to be dx1, or I will write it as x, I plus d phi dy j plus d phi dz k. That's the meaning of it. And you can extend this idea to cylindrical or spherical coordinate system. The key point here is that the gradient itself, when it acts on a function, it's going to generate you a vector. A scalar function, right? It can also apply to other stuff too. So in Einstein notation, sometimes a gradient, we define it as a dd, let's say, dqi ei. So let's consider it as an orthonormal coordinate system, right? So you can use that. It's the same thing, considering the HIs are 1. So important point about the gradient is that always the gradient vector is normal to the level surface phi. Always it is perpendicular. It's very important when you are dealing with irregular shapes and you want to find the normal direction to the surface, right? So let's say last year I asked this question in the exam actually. So they needed to, for some calculation, they needed to calculate the normal to the surface of a spherical droplet, normal vector. Okay. Can you guess in which direction it is or what it is? Unit vector. Tell me a unit vector that is normal to the surface of the sphere. At all points, right? So think about this, or circle. 2D is going to be circle. Maybe that's easier, right? I'm looking for some vector like this. Always it is normal to the surface. It is defined like that. But that's the general idea, right? So if I can define an equation for this sphere, right? So let's define, what is the equation for a sphere? That's it, right? So for a sphere, you have x squared, y squared, z squared equals to r squared, and this means that the center of the sphere is at the origin, right? So if you define a function like that, basically you can define it phi like r squared minus x squared minus y squared minus z squared. So that defines your surface of phi. Level surface is phi at 0, let's say. So if you calculate the gradient of that function, that's going to give you a unique, basically, vector here. And that vector is pretty simple for a sphere or circles. It's going to be in the radial direction. It's your r hat vector. So basically, if this is the origin, so this is r hat. So in a 2D case, it's going to be xi plus yj divided by x squared, y squared, and square root. But you can extend that to the 3D. It's exactly the same thing. So when you go home, calculate that. Calculate that basically a vector using the gradient of the surface of a sphere. Make sure you get that r hat. You see that r hat. If you work with the Cartesian coordinate, you are not going to see r hat. All the expression is going to be based on x, y, z, right? But you need to basically make sure that this, whatever vector you get, it's like this: xi, yj, zk. Z square, right? And this is basically your R. So that is the vector that is always perpendicular to the surface of the sphere at any point, x, y, z. So yeah, so the perpendicularity is very important. Also, we use this gradient when we want to optimize the processes. So it always tells us basically the direction that the changes are happening, or the basically steepest descent direction. So we will talk more about this basically vector operation in the next class. Now, I think it's a good time to do a short quiz.